Naszym pierwszym prelegentem jest Paweł Cichocki, który opowie, jak skalować blockchainy pod względem technicznym.
Halo? Cześć. Dzięki, Olaf. Dobra, to zacznijmy sobie od tego, co już zaspoilowałem niestety. Blockchainy są wolne. Ktoś wie, ile transakcji na sekundę robi Bitcoin? 7. Otóż nie, 7 to on chyba nigdy nie zrobił tak naprawdę. 7 to jest teoretyczny limit. Ale tak. A Ethereum? Nie? Dobra, Bitcoin 7, no do 7, więc dobrze. Kurczę, panel ekspertów. To nie wiem, może ta prezentacja będzie zapostowowa dla was. Oh, by the way, everybody wants Polish? Or anybody opting? English. Okay, I'll talk English for people that speak only English. Okay, so the presentation's in English anyway, so you'll be able to follow along. So why are the blockchains slow currently? Most blockchains are slow. Why? Well, there's a single blockchain for most cryptocurrencies, and all the transactions from all over the world need to meet in a single block. In a way, it's centralized. I don't mean to say that a central organization runs it. That's what blockchains abolish. But as a data structure, it's a singleton. Or everybody tries to have the same blockchain in the end, right? Each miner tries to have the same history. With such a solution, the speed is simply block capacity over block time, right? So basically, all the transactions go into a block. For Bitcoin, that's 1 megabyte currently. Anybody heard about the 2x proposal? Sometimes referred to as SegWit 2x. Yeah? Who heard about that? Yeah, okay. A knowledgeable crowd. Good for you. So what they tried to do is basically make that bigger, right? So that would be twice the speed. So for Bitcoin, it's 1 megabyte currently. A transaction takes approximately 250 bytes. So that gives about 4,000 transactions over 10 minutes. Something like 6.9997 transactions a second, right? Okay, so why don't we just tweak the parameters? Why don't we just, make 1 gigabyte blocks over 10 seconds? Anybody starting to see the problem with that? Can't reach consensus, exactly. Consensus, if you had few nodes, you could, right? But if you want many miners to reach consensus, they have to be able to keep up. And they have to be able to keep up from many perspectives. So what are the limiting factors currently? So there was this cool paper called Information Propagation in the Bitcoin Network that was done by Christian Decker and Roger Wetterhuffery. I hope I pronounced that right. Pretty cool guys. And they basically researched peer-to-peer networks, mainly the Bitcoin network, and that's what they came up when they measured basically the delay over the size of a block mapped onto the block size. And basically, for bigger blocks, this stays constant. So basically, the bigger the block, the slower it gets transferred to other nodes. So, initial headroom is for, just starting the transmission. So it's pretty obvious it peaks up here, right? And then there is the speed of a min-spec miner, somebody that we want to be a miner, to verify a block. And let's say for smart contracts, it's even worse. But for dumb transactions, as I like to call them, it's well, $1,000 2015 hardware PC verified them at about 1,000 a second. So up to 1,000 a second is easy with one single computer, a multi-core machine, but not much more. So most cryptocurrencies don't reach 1,000 a second. So this part is critical, right? So what happens if we don't transmit a mined block fast enough is basically we get forks, and that are not forks like in Bitcoin. We had hard forks where basically one blockchain got split into two. It's more like blocks. One part of the network starts mining with exactly the same protocol. One part of the network starts to let's wait that starts to mine from one block they got, and the other part starts to mine from another block they got. Each node is obliged to basically mine from the latest block, right? From the longest chain they had. So we get forks, and then it takes longer to verify that a block is indeed in the blockchain. So the whole, we don't get an acceleration because, okay, we might have more blocks or bigger blocks, but we need a much bigger time to verify them, right? For big Bitcoin transactions, people say you should wait 6 blocks. If we would have many orphans, that would be much more, I don't know, maybe 100 blocks. So the whole point is you can't just tweak the parameters. All right. So are there any solutions that people are working on? So we have solutions on many layers. One layer is the fundamental layer. So we're trying to make the blockchain faster, just more transactions. But there are also solutions, and the most popular is Lightning Network, which can be used basically with any of the above, but doesn't really put most of the transactions onto the blockchain. So it's a second layer solution, and we won't concentrate on that. Unless maybe you guys, who heard about Lightning Network? Everybody, okay. I think this is too basic for you guys, maybe. Okay, so I'm gonna go over a few solutions. I'm gonna start with Ghost, which is currently used in Ethereum. That's why Ethereum is basically 15 transactions a second, so twice the speed of Bitcoin. And then we'll move to Bitcoin NG, Ripple, and IOTA. And there's some always new solutions that claim wild things. Hashgraph is one of them. They basically, their paper is very not clear, so I'm not gonna discuss the solution, but you have to watch for snake oil. Okay, so what's Ghost? Ghost basically takes the idea, this is what a blockchain looks like, right? Oh, so the yellow nodes are orphans. So that's what happened when we had even well-meaning nodes, but the network wasn't fast enough, right? So a part of the network continued from this block here, right? And another part continued here, which was just orphaned later. So some wasted energy there. So people said, why not just use a DAG, a directed acyclic graph, just like in Git versioning system? And well, that's how it works basically. You have blocks that don't have just a single ancestor. They take many blocks as parents, and they get rewarded for it. In Ethereum, it's called uncle reward. And well, that makes the oops. What happened here? All right. Wait. All right. So that's how Ghost works like. All right. Then there's Bitcoin NG. So this is a picture I think sums it all up from their white paper. Basically, what what they want to do is they want to assign nodes that will drive the network forward for a period of time. So in this case, 10 minutes. So you have, when somebody mines a block, they're responsible for then signing small sub-blocks with a few transactions. And basically the reward for a block gets split among those transactions, and some of the reward goes to the winner or miner of the previous major block. Some of the reward goes to the next one. And those rewards that can be taken away should prevent cheating. But just so we get to the base of the idea, the basic idea is let's concentrate the network to a single node that gets switched very often, and that network can go faster than when it synchronizes with the rest of the network, right? So we sort of delegate the work to one node. I think Waves implements the Bitcoin NG protocol now, and they have about 100 transactions a second. So it's pretty impressive. Okay, then there is Ripple. Ripple also tries to delegate some of work to special nodes. They have special servers, so not everybody can be a server. There are servers, there are clients. Servers exchange among themselves a special unique node list. And basically they keep a ledger open. It's not even a blockchain. Ripple is not a blockchain. That might be important to assert here. The servers just vote whether the current state of the ledger is fine or not. And they have a mechanism where they see if the network is still connected. So they try to prevent a split up, so that all the unique nodes see each other. It's fast. It gets many hundreds. It can support up to many hundreds of transactions a second. The problem is we don't have a proof of work here even, and people have to rely on those servers, on those unique nodes, to be fair, basically. And to prevent Sybil attacks, not everybody can get a master node or a unique server, whatever they call it. So it's not really, decentralized. You have to have some trust in the owners of the network or in the servers. All right, so then we have something very interesting that's called IOTA, Tangle. So they came up with a structure they call the Tangle. The Tangle it's not a blockchain. Each transaction in the Tangle has basically two parents. So each square here represents a transaction, and you'll see it has 2 hours that go to another transaction. Each transaction is additionally secured by a little proof of work, but the proof of work doesn't scale. So the community welcomed this quite coldly because, well, the basic problem is the whole network could be overtaken. This is designed, as the name suggests, IOTA is for the Internet of Things. So the first use case planned was the use for small devices, where the value of the transactions probably is not that big. The proof of work here doesn't scale. Each transaction basically requires the same amount of work, and to prevent very easy overtaking of the whole network, right? So if we have this Tangle built by small devices, somebody could connect some big servers and overtake this whole Tangle with a side Tangle, right? And then do double spend. but to limit that, they also have a limit on the size of a transaction. So it's an interesting concept, but the security of it is very much disputed. All right, so I'm here from Nebula Network. We have one solution too. And let me tell you about that one. So let's take a step back and think how the network operates. By the way, I assume you all guys and girls are familiar with things like proof of work, right? Who knows about proof of work and could explain it? Okay, I know, but I can't explain. Okay. All right, so let's talk about proof of work for a second. So the network, each blockchain lives basically on a peer-to-peer network, something like BitTorrent or Emule. And the nodes send each other transactions. Those transactions get collected into blocks. A block gets tied into the blockchain, or as some Polish people call it, klocko-łańcuch. And the link is via a hash, a cryptographically safe hash. So the blockchain further down the road is immutable. You cannot swap a block, right? Or maybe let's show a picture of a blockchain. We had one here. Oh, right. Here's a nice one, right? So, so the transactions get into, and we had a slide for that too. Right here, right? So the transactions get into a block. The block gets signed by someone, and everybody builds on top of that block, the next block, and so on. So how do we choose who signs the block? Oops. There was, all right. Well, basically it's a lottery, the basic. And the lottery is similar to democracy, right? Because if everybody gets picked once a while, it's like everybody has a saying, right? But somebody evil could introduce many nodes into the network. It's cheap to introduce new nodes into the network. That's called a Sybil attack. And those nodes could take part in the lottery, so cast a vote. And basically they would have more influence. So to prevent that, actually it was Satoshi Nakamoto, I think, in his original white paper, the Bitcoin white paper, devised a scheme called proof of work. So each node, to sign a block, has to perform some work. So to perform some work, some computational work, you have to have a CPU. If you connect 1,000 nodes on one server, or you simulate 1,000 nodes on a server, you still have only as much voting power or as much luck in the lottery as you have CPU power. CPU power is expensive, so to overthrow the network with your nodes, you have to overthrow it with computational power, which is expensive. So that basically secures us against Sybil attacks. So the basic idea is you have to prove, each node has to prove it has some value. The easiest thing to prove is computational power, right? We don't have to, check if somebody has, say, some gold under the computer. That would be difficult, right? It's difficult to check for value with computational power. Okay, so let's skip ahead to this. Yep. So the nodes of the peer-to-peer network verify the blocks, right? And a simple solution in a decentralized system is everybody verifies everything. A solution where everybody would trust everybody is everybody verifies just one transaction, or everybody gets their part and they, but we don't trust everybody. So, so to make it quicker, like in Ripple, for example, we can select a few nodes to verify the state of the network, to verify the transactions. Those few nodes can communicate quicker, be on very good machines. So it works, but it's still limited, and we have to have trust. So, so that's not a perfect solution as well. Another solution we can think of is to have a redundancy between the, everybody verifies everything, and people split the transactions and everybody verifies just their set. So we could verify selectively and have many eyes that look onto the network. And that's how we try to do things. But to make it work, you also have to have incentives. In Bitcoin, for verifying the transactions, for trying to mine the blocks, you get a block rewards. We get Bitcoins for securing the network. To incentivize, to motivate people to look on the selective parts of the network, you still have to motivate them. So that's important. We'll get back to that too. All right, so our basic idea is, instead of having a single blockchain, we have many blockchains. So the idea is that each address lives on one or a few blockchains. And they basically look at those blockchains and verify those blockchains that they are part of. I can hear anybody see a problem with that already? Because there was a slight problem we had to solve. Basically, the security is a problem, right? Because if you have a single blockchain, everybody looks at it, and all the proof of works goes into one blockchain, right? So with say 2 smaller blockchains, each blockchain would be half as secure, right? From the Sybil attack we talked earlier. So to prevent that, we have a few things. First of all, we don't use proof of work. We use proof of stake. Anybody heard about proof of stake? Heard about proof of stake? Okay, many of you. So proof of stake is a very similar concept to proof of work. You still prove value, that you have value for the node, but the value you prove, it's a self-referential system in a way. So you prove that you have value by just keeping some currency, the cryptocurrency that the network operates on. So you don't have to burn in electricity. It's pretty green, the technology of proof of stake. All right, so what we can do here is basically sync those chains in the master chain, where it's a very small chain. We just put the hashes of the blocks. We put hashes of the blocks that to make to avoid basically orphans in the master chain, which would be problematic. I mean, we can solve them, but it slows the whole network down, so we want to prevent them as much as possible. We just put small hashes of the blocks that are pretty sure that are verified into the master chain. And basically, who can put the hashes of the blocks into the master chain? Just the people that have stake in all the subchains that get synchronized. So on a single subchain, the transactions are very fast. Some transactions that go over many subchains are slower, but our assumption is not all transactions are made equal. And if we can make everything faster by desynchronizing our solution, let's do that. So if you pay for coffee, well, you want an immediate transfer of funds, right? Coffee gets cold. But if you send money to Australia, if you wait a few minutes or even an hour, it's still way faster than through the banking system. And well, usually you send a little more money. It's fine for you to wait till the transaction is confirmed, right? So If you can, don't make the transactions across the counter wait for transactions across the continents. All right, so there are a few problems. Some of them we still work on. So one problem is how do we create split side chains? Another problem is how do we make the side chains secure? I already touched a little bit on that. And how we transfer funds between the addresses that do not share a subchain, right? There are a few things we are experimenting with. So one thing is if a subchain has many transactions and the transactions start to wait, we can split it automatically. So one way is just completely random. A better way might be by clustering those addresses that transact with each other more often, but we're not sure if the security of that is still as good. We don't see anything wrong with that, but we're still investigating if that's a good way to do it by clustering. And of course on demand, so people can just declare that they're starting a new subchain and transfer funds to it. So we're also considering a block mesh, so something like the Tangle, but instead of transactions, we do blocks. But that's a research project we're not ready to discuss in more detail right now. Okay, so how do we make the subchains secure? How do we make... we basically use proof of stake, but we use it in a modified version, which we call proof of collateral. So originally, proof of stake was just signing the blockchain. You had you had more probability of being able to sign the blockchain if you had more stake or more currency. Then there was a system called coinage, where basically if you have a coin, say you have 10 coins on your account, then after one iteration, after one time period, your coinage is 10. Then it's 20, 30, and so on. And it grows until you sign a block. Then it falls off to 0 after you sign a block. Why like that? Because if people had little stake, all the big stakeholders were signing all the transactions, all the blocks, and that was perceived as a concentration of power, right? So so what's proof of stake in the proof of collateral mode? Well, we think what they could do, or we can do a little better, is instead of holding the coins and then signing the block, we can first lock the coin for a certain amount of time when signing the block. With that, a pretty cool side effect of that is if you detect a double spend, or if you detect that somebody signed 2 blocks which have a double spend, you can take the funds away. So basically, if you can, and there's also one thing which prevents us from signing many, because a double spend can be a multiple spend. So we have an algorithm that prevents people from signing many blocks. Basically, we take the hash of the block into account when saying who can sign the block. If someone detects that somebody signed a double spend, the people that received the funds can be reimbursed from the collateral, from the basically locked stake, right? So we don't make people wait with their stake. We lock it straight away, and then wait. It can't be used for anything for a certain time. All right, and then to prevent long-running attacks, we put the hashes of the blocks into the master chain. All right, then there is a question how to mine the stake in the master chain. So one idea we work on is basically if an address, if somebody wants to put the hash of the block of a subchain into the master chain, they have to have stake in that chain, in that subchain. And the rest of the network can look at that. Other people can look at that subchain. And if they detect that it's cheated, basically, that it's not a good block from that subchain, again, proof of collateral makes it easy to take the funds away from the cheating node. Well, and to bootstrap the network, we plan to put the hashes as well into other established public blockchains. So Dash, Bitcoin. Bitcoin might be quite expensive. Ethereum. Now there's this project called Polkadot, which makes that easy, actually, which is a pretty cool project. Who heard of Polkadot? All right, some people as well. All right. So how do we transfer funds between addresses that do not share a subchain? Well, we have two operations called teleport out and in. So basically, the funds disappear on one subchain. When it gets synchronized to the master chain, we're pretty sure that the block that had the teleport out is valid, right? And then we can use a teleport in on another chain. But that's not all. Of course, we can use solutions like the Lightning Network. So basically, if we can find a node that is willing to precipitate and has funds on both one subchain and another subchain, we can transfer through them. So it's basically like an analogy would be, say, you have a grandmother in Poland and you work in the States, right? And sending money is problematic sometimes. So in a normal banking system, you just ask your friends, which is an account both in an American bank and in a Polish bank, and say, hey, I'll send you like $100. Can you send 400 zlotys to my grandmother in Poland? Basically, that's how Lightning Network works a little bit, and that can be done as well to communicate cross-chain very cheaply. All right, so that's it for my talk about Nebula Network. Any questions? All right, so Lightning Network. Sure. So Lightning Network is the second layer protocol where first you establish a secure communication or you establish a common fund between two accounts. So let's say you and me, we want to exchange money, right? So say on the Bitcoin network. So how we could do that is we both put in 10 Bitcoins into a shared account, so to speak. And then if I want to pay you 2 Bitcoins, I send you a signed update of the balance that says you can take out 12 Bitcoins and I can take out only 8, right? So it's like I would transfer 2 Bitcoins to you. If I want to transfer 2 more, then we update the balance again. You have 14, I have 6, right? If you want to pay me 4 back, we update it back to 1010. Those transactions, we can exchange off-chain. So they don't have to fit into those blocks. So this formula, speed is block size over block time doesn't apply. Before we can close the shared account, there is a grace period. Currently, it's proposed to be, I think, half an hour or something like that. So basically, if you want to withdraw, right? So the account balance was 14.6 for you. And you want to withdraw the funds. You can do that at any time, but you have to still wait half an hour. And during that half an hour, if you have sent me before an update that it's 1010 again, I can go like, wait a second, I have a newer transactions. And those transactions, those off-chain transactions are numbered. So, and the number, their index, is also signed, right? So I can say, hey, I have a newer transaction that says I have 10, not 6, right? Of course, if during that grace period you closed the account, then, well, good for you, you took my Bitcoins, right? So that's how we establish a channel one-to-one. We can do as many transactions as we want within those, 10 Bitcoin limits, right? But it's only one-to-one. And we need 2 transactions, one on the blockchain, one to open the channel and one to close it, basically. And maybe some more to, to say, hey, no, that's not the last transaction. But everybody works with the protocol, doesn't cheat, then just 2 transactions, right? So I assume we wouldn't cheat each other, so it would be 2 transactions, open and close. And then, if we have such channels, say I want to send some Bitcoins to Justyna over here. Justyna, say hi. All right, so I don't have a direct channel to Justyna, but you could have, right? So I basically say, hey, I'll send you 2 Bitcoins, you send them to Justyna. And what we can do, I can give a secret to Justyna, and we can sign the transactions in a way that only when you get the final secret from Justyna, that my transaction to you and your transaction to Justyna is valid. So you cannot cheat me. So I send you 2 Bitcoins and you don't send them further because you don't have the secret from Justyna, right? So as long as you don't have that secret, my transaction to you is only speculative. And the transaction is off-chain. So if we form a network this way and we find a routing protocol, we can basically send a lot of money, a lot of transactions off-chain. The only downsides are, well, you have to lock some money, right? Again, and it's sort of funny that no matter from which side you bite the problem, a similar things occur. So, for example, making the blockchain faster, we found out we have to lock some stake, right? To use proof of stake, not proof of work, because it helps us to make the system better. Here, if you use Lightning Network, again, you have to lock some capital. So it's in a way similar to proof of collateral, right? You have some locked capital. Then another problem is if you don't find a road for the money. So for example, if I want to send a lot of money to Justyna and your channel with Justyna is not big enough, then I'm out of luck. I just have to do a normal transaction through a blockchain. All right, so if you have a lot of transfers, they're one-sided, one-directional, then those channels will deplete as well, right? So if you opened a channel with 10 Bitcoins and then you want to send me 100, well, we're out of luck, right? So there are some limits, but overall, Lightning Network is very cool, and for smaller transactions, it can be very fast, right? Yes, there are fees. All right, so the question was, are there any transaction fees? Do you get anything from signing the transaction? Yes, so in our system, yes. Generally, in most systems, you need to pay a transaction fee. So in Bitcoin, for example, the transaction fee is voluntary. And because the network is slow and you want yours to be, queued by the miners into the block faster than the others, you make it a little bigger, right? So the transactions that have the biggest voluntary fee get mined the fastest. So that's maybe also why politically some miners didn't want the 2x extension on Bitcoin, because that would make the blocks 2 times larger, the network 2 times faster, the queue would be smaller, and transaction fees would go down, right? So in proof of work systems, miners burn electricity, right? So that's the cost. So to offset that cost, for now you have the block rewards, but say in Bitcoin, after some time, the block reward will drop to 0 to assert that there's a finite amount of Bitcoin. And to offset the cost for the miners, well, they have to be paid somehow, right? So you have to have transaction fees. Here, people in proof of stake systems, people lock their capital, right? If you lock your capital, if you put it into a bank, well, you want to gain something from it, right? So here too, you have to reward people for locking capital. In IOTA, you have no transaction fees, but then the system's not really secure because it can be, overtaken by a powerful player. So, there are various things to consider, but basically you can't have a system. There is no free lunch, right? So if you want to secure a system, it has to cost something. Just like in the physical world, if you want to lock doors, you can invest in a good lock. All right. Anything more? Yes. Yes, so if you have a few blockchains, right, and each, say, for the sake of argument, supports 10 transactions a second, right? So if you have 100 of them, that's 100 times 10 transactions a second, so 1,000, right? So basically, what our blockchain is doing is scaling, right? The more transactions you have a blockchain that just a part of the network that just spills transactions left and right, and it's too much to handle for a single blockchain, it gets split. So when we come back to this, maybe let me go back here to, right, the basic problem was here, right? So basically, you have to transfer the block to the whole network, and basically, the bigger the blocks, the bigger the delay. But if you have subchains, you don't have to transfer to everybody. You just transfer within your subchain. You transfer to everybody who's in the subchain, right? You don't have to synchronize with all subchains. You don't have to verify transactions from all subchains. So every address can be on a few subchains. They verify the subchains. And when we talked about how to make it secure and scalable, everybody looks at just a part of the network. So this part is, in our case, the subchain, right? So many eyes look at each part. You can choose even on which subchains you want to have your funds. Yes?
What is the connection between the master chain and the subchains? What is recorded on the master chain?
The master chain basically contains mostly hashes of the blocks from the subchains. It contains also the stakes of the people that signed the master chain. So basically, they declare what their stake is, right? And they can be then, verified and quickly, punished or discarded. And it contains declarations of the teleport operations. So basically, if somebody,
basically all hashes for all the blocks from the sub blockchains and
just the hashes,
and
hashes and stakes, and
okay.
practically no transactions.
Any question?
Yeah.
Thanks.
Thank you.